All right, y'all. Let's solve some problems. So the good news about Freefall is it's very, very similar to what we just got done doing with horizontal motion. And you guys are doing a great job with horizontal motion. So keep up that work, keep going, and just think about these as vertical motion as opposed to horizontal motion. But it's the same equations, okay? Same knowns and unknowns. You're just going to have to draw the pictures a little bit differently and set up things just a little bit differently. But we'll show you how to do all that good stuff, and we'll work our way through all of it here. So a rock is dropped off a cliff into a lake. You hear it splash into the water 3.2 seconds after you release it. Draw a picture of the situation. List all your knowns and unknowns. How high is the cliff from which you drop the rock? How fast is the rock traveling just before it hits the water? So we've got our same equations up here. Old Faithful, Big Chalupas, Ain't Got No Time. And then I've got a reminder of what the value for G is, which is 9.8. So we're going to start by drawing the picture. Here's my cliff. Here's the water. Here is the rock. It's going to fall down. Okay. The only value it gives me in the problem is time. So I'm just going to write time off to the side here. T equals 3.2 seconds. And that's it. That's all I can do in the picture. Other than draw the object and the direction it's traveling. That's really all I can do so far. So we're going to have to figure out some more things. But this is the starting point for the picture. Okay. List your knowns and unknowns. Well, it says you hear it splash into the water 3.2 seconds, so T equals 3.2. And it asks you to figure out how high the cliff is. So how high the cliff is a displacement. That's how far it's going to fall. So we're solving for D. But we're in trouble here because we don't know VI, we don't know VF, we don't know A. So A is the acceleration, VF is the final velocity, and VI is the initial velocity. So we need to start reading between the lines to see if we can figure this out. So the first word that you want to be careful of when you read is the word dropped. So dropped is different than throw. If you throw something, you give it an initial velocity and send it through the air. If you drop something, you just let it go out of your hand, which means the initial velocity is 0. So if you see the word dropped, that is meaning initial velocity of 0. Or if you say it says it's dropped from rest or starts from rest or anything like that, that'll tell you the initial velocity is 0. So that shouldn't be that surprising. And in fact, I bet a lot of you probably could have guessed that on your own, but I want to make sure to point that out, that that is something you're going to see there. And here's the more important one, and it's the easier one to miss, but it's the one that is always going to be there. Why is this thing falling? Because gravity exists. Gravity is down. And so because gravity is down, it's going to fall down. And so we do know the acceleration. The acceleration is g. The acceleration of gravity. And that value is 9.8. Now you notice I didn't use any negative numbers. And that's because it's really important that you draw the direction of motion, because that is positive. So I am I'm dropping this thing, down. So down is my forward direction, which means G is positive, which means the displacement on the way down is positive. Everything is positive down because that's the direction of motion. So how high is the cliff from which you drop the rock? So we have D, T, VI, and A. We didn't say anything about V final, so I'm leaving it blank for right now. I'm not even putting a question mark because I'm not asked to solve for it. So I'm looking at my three equations. Old Faithful has VF. I don't know VF, so that one's out. Big Chalupa has D. I'm solving for D. VI, I know VI. T, I know T. A, I know A. So Big Chalupa is the equation we're going to use. So D equals VI T plus 1/2 a t squared. Again, notice everything's positive because the motion is forward, down, and down is the forward direction for this problem. So 0 times anything is 0, so this goes away. D equals, so I'm going to go ahead and square the 3.2, and I'm going to multiply 1/2 times 9.8, so that gives me 4.9 times 10.24. When I multiply those out, I get 50.2 meters. And that is my displacement. That is how tall it is or how far it will fall. Perfect. So now, how fast is the rock traveling before it hits the water? Now, the key word is before it hits the water. So we are solving for V final, but it's not 0. This is not after it hits the water and stops. This is right before it hits the water. So I need one of my other equations that has V final in it. Ain't Got No Time has V final in it. Old Faithful has V final in it. It does not matter which one you use because you know everything else now. You know VI, you know VF is what you're solving for, A and D. So you also know time as well. So you can use any of those. I'm going to use Old Faithful because it's the easiest. So V final equals V initial plus A times T. And 9.8 times 3.2 is 31.36 meters per second. Now, I want to do one last setup here for y'all, and that is what happens if you throw the object up. What is going to change? So I'm going to use the exact same problem, but instead of dropping it, I'm going to go ahead and say that my initial velocity is 10 meters per second up. So if I redraw this picture here, here's my cliff, here's my water, here's my object. The object is going up now, and it's going to go up into the air before it turns around and comes back down. And let's go ahead and use the same time of 3.2 seconds, and let's go ahead and write our velocity of 10. So here's what is going to change when you do things that are vertical motion. So the first thing that is going to change is the direction. Now, up is the forward direction, which means we still have gravity, but it's a negative g because it's in the opposite direction. So g will be negative if I throw something up rather than letting it fall. And that's on the way up and on the way down. On the way up, we have positive motion, g is negative. On the way down, we have negative motion, g is negative. So make sure you always keep g negative if you are going up to start with. Not with what we did here. Here, g is positive. But here, when we started going up, g is going to be negative. The other thing I want to point out is there's a very special point, and that is the highest motion. So the object's going to go up, going to go up, going to go up, going to go up. It's going to reach the highest point. It's going to turn around, and it's going to go down. And then it's going to reach the ground at the bottom. This highest point is a really special place. And the reason it's very special is because there is something that is always true here. And that is this. At the max height, V equals 0. And that's usually going to be your V final, but I suppose it could be your V initial depending on the problem. For example, we're starting at the max height here and dropping it. So the max height is going to be a velocity of 0. It is always a velocity of 0. So you get to a problem on practice 3 when it talks about what's the max height the ball reaches. One of your known values is going to be V final equals 0. And the reason for that is because at the max height, You know the velocity. The velocity is 0. Other than that, for free fall on the way up, it's the same setup. You're still using these equations. You're still using g to be 9.8. You're still doing your knowns and unknowns. So if I were setting up this problem, I have an initial velocity, I have a time, I have the acceleration of gravity, and I'm solving for the displacement. I would use the exact same equation that I was using before. I would use big chalupa, so I would say d equals VI t plus 1/2 a, which is negative 9.8 this time, and yes, you got to be careful about that, t squared. So you can see I'm using the exact same equation. The only things that changed are I have an initial velocity because I threw it up, and I have a negative gravity because I started up, which means gravity is negative, the opposite direction going down. Okay? That should get you what you need to get going on the practice. Number 1 is just drawing a diagram and trying to explain what's happening on the way up and on the way down. We've done this in the notes already a little bit, so I want you to see what you can do on your own. Then you're going to do a free fall problem where you're going to solve for the height of the cliff and how fast the rock's going before it reaches the ground. So it's going to be very, very similar to what we did, but the numbers are going to be different so you can get some practice there. Then you're going to do another free fall problem, and then you're going to do one problem on the way up. Do the best you can on these. Show your work, draw your diagrams, do all those things that you need to get the full points for them. And show me what you guys can do. Again, we will go through these next time, and we'll talk about them then and see if you have any questions.